Well, greetings today, Better Break audience. Today we will be talking about entropy. This will be the last edition of the year. And, well, we'll try and get right to it, as this is quite a big topic overall. We ended up coming to this topic after discussing it with multiple of our students. We get a bunch of bio students, chem students, physics students. And what we ended up realizing is that we all disagreed on what entropy was. We had also a communication science student, and when she asked about us what entropy was, we all came with our own little answers and just great disagreement. So today we will have three speakers discussing their ideas on entropy and hopefully elucidating the topic more for the general audience. I will be assisted by my friend Avo Rapero, and that is in general this idea of the talk. Debate Break, for those who are here for the first time, is a discussion platform. We host talks monthly, and we try and, generally speaking, explain the idea of our topic to a more general STEM audience. The talk will be structured in three parts. We will be talking about we will first introduce the concept of entropy to you all, where we will have the speakers just give a brief description of it in a way where you can immediately understand it. In the second part, we will talk about the contentions between the differing entropies. And at the end, we will just talk about the future of entropy, and we will also try and tie some loose ends. Feel free to have as many questions as you want. It's a difficult concept.
Thank you, Saad. Well, I am the other moderator. My name is Alvaro. My background is I am a biologist. I have a bachelor in biology by the University in Cordoba in Spain. And this is my third edition in the Beta Break. I've been a 2 years member. I've been part of the Religion and Science edition and Female Orgasm edition. And we're looking forward to go down to the entropy. I want to welcome our speakers, Greg Stephens, Christian Schaffner, and Esther Kadekers. Would you like to introduce yourself, Greg?
Sure. Well, first, let me thank the organizers and everybody out there, wherever you are, for this chance to have a discussion with everyone about a topic that's a concept that's very dear to my heart and my research agenda. I'm a theoretical physicist at the FU, working in theoretical biophysics, thinking about how to build theories like we're used to in non-living physics that are as successful in complex systems like living matter, especially on the scale of organisms. I'll show you a video when I go over my slides. So it's a pleasure to be here.
Thank you. All right. Do you want to introduce yourself, Esther? Oh, your mic is off.
First of all, I would also like to thank you for inviting me. I'm happy to be here to talk about this subject that is also very important in my work. So I am a big historian. What does that mean? That means that I teach about and also do research in a type of history that covers, well, everything we know about the past. So a type of history that spans everything from the Big Bang to today. And okay, of course, you cannot study all of that, but what you can do is use that perspective to try to see if you can find some new patterns or come up with connections that are easily overlooked if you look at history in a more focused way. And I think one of the patterns that immediately emerges when you look at big history as a whole is a pattern in which entropy plays a pretty important role. And we'll probably get to that later.
Perfect, thank you. And our third speaker is Christian, who has already participated with the Beta Break once. Am I right, Christian?
Yes, it's been a while, but I've been on one of the panels before. So my name is Christian Schaffner. I'm a researcher at the Institute for Logic, Language and Computation in the Beta faculty of the University of Amsterdam. I do research on quantum cryptography. So on the one hand, we have quantum effects, quantum computing, that maybe gives us new capabilities in terms of what we can do with this new kind of computers. On the other hand, cryptography studies like settings where people don't trust each other. Maybe you want to keep some information, and we already have a word here, information, a secret from others. And that in the future, maybe we even want to protect our quantum information from others. So, and in my work, I use entropy as a tool to kind of quantify how much people know, how much information they have about certain things. And in this context, I'm also teaching a course on information theory, where entropy plays a very central role. And I'll be highlighting kind of the mathematical definition of it later in this hour. I'm looking forward to it.
Perfect. Thank you. And now, last but not least, we want to give a shout out to another colleague of us from the Beta Break, Frank, who will be in the shadows moderating the Q&As. So if you have a good question, just throw it out there and he will direct it to us. We will answer it either live on the talk or maybe right after the talk in the Q&A section. And should we go for it? I believe that we want to start with a brief introduction on the history of entropy.
Correct. So, well, let's start with that. Entropy all the way at the beginning. Esther, would you like to do the introduction?
So I'm not sure if I am the person who is supposed to talk about this. So the history of the concept of entropy and the definition of entropy. I think there was another slide by another person who was supposed to talk about that. Am I right?
Yeah. Greg, do you want to talk about it rather?
Sure. I think I have a slide that works well for this. Okay. So let me pull up I'm going to share my screen and pull up the slide. Okay. So first of all, everybody can hear me and see the slide? Yes?
Yes.
Okay. I don't know if I'll capture every last element of entropy. And so I'm hoping my colleagues, Christian and Esther, will jump in if I miss anything. But it happened that when I was thinking about this beta break, and I came across this beautiful graphic, actually. This is from a book. It's not my own graphic. Maybe some of you have seen this before. And this is from, sorry, I have to move my screen around a little bit so I can see everything. Oh, my screen, I can't see the bottom. Anyway, I think, can you see the bottom of my screen with the reference? I hope.
You mean Newman 1940?
No, you can't see the reference. Oh, that's too bad. Okay, let me just try one more thing because that sizing isn't going to work. Sorry.
We saw this one line appearing from entropy something.
Yeah, okay, maybe we have to do this. I don't know why that's not showing up. So let me try this one more time. Could try the full screen, but I think that's not going to work. We'll try that once. Still not showing up, right?
I think it is.
Yeah, now it is.
It is. You can see it. I can't. Okay. All right. So you can see the reference. I just want to make sure that reference is adequately floated. Okay. So entropy's been around for a while. I'll get to sort of its thermodynamic origins in the time of our industrial revolution, hundreds of years ago now. But I wanted to go over this sort of set of different formulations of entropy because I think this will at least partially capture the different perspectives that we're going to hear from today. So I'll go through the thermodynamic origin of entropy in this force formula. S is equal to dq. That's the heat that's flowing into a system at this is reversibly at temperature T. For those of you who can remember back to either my class in statistical physics, or maybe you had a class in statistical physics, you will recognize the Boltzmann formula for entropy as the log of the number of degenerate microstates, W. Maybe we also introduced this, it can go under the name of Gibbs or also of Gibbs and Boltzmann. If the different states are in a canonical ensemble, the probabilities of different states are actually unequal. So instead of just one W, you have a probability or a frequency I for each one of these states. These are very similar. And then we make a really big conceptual jump. Christian will tell us about this, where all of a sudden we have a very similar looking formula for entropy, but coming out of a completely different direction. This is from Shannon and information theory, but looks very similar to what we had in thermodynamics if you replace, if these P's, if you just allow P to be a general probability distribution instead of coming from one of the thermodynamic ensembles. I know that there's more notions of entropy that aren't captured in this particular graphic. One of the ones that we work on that I want to mention is there's even a notion of entropy, not in a probabilistic system, but in a totally deterministic dynamical system. That's a notion, it's called the Komogorov Sinai entropy after the founders. And it's the idea that a chaotic dynamical system, which is completely deterministic in its rules, can generate uncertainty by the nature of its chaotic evolution. And I will come back to that, and when I'll show you some relevance of that dynamical entropy in some of our work in studying animal movement. Okay, so let me then go to the historical origins of entropy. And again, back probably even to high school for some of you, you might have been first introduced to entropy when you're thinking about these things, steam engines, a long time ago, right? And in the time of the Industrial Revolution, there were really important engineering questions about how you can turn heat sort of that you generate from boiling water, from burning coal and boiling water. How can you turn that use that hot material to drive a mechanical process and do work? And this is one of the interesting examples, I think, in physics, in science, where you have what is a very applied problem that intersects a very deep question.
Sorry to cut you, Greg. I think we're in the wrong slide.
You haven't changed slides.
No, we're still in the entropy.
Oh, okay. Then I have to go back. Okay, sorry. Hold on.
No worries.
Thank you for that. Let's do this again. Sorry. I think it's the desktop versus the. Okay. Now you should be on the steam engine slide.
Yes, now.
Yes.
Thank you.
Okay, good. Entropy in the talk. So back in the time of the Industrial Revolution, the important societal engineering sort of industrial challenges were how to turn sort of heat that you generate by burning coal and boiling water into mechanical work that you can use to drive a locomotive or can drive an engine in your factory. Very important. How do you make this as efficient as possible? Sounds like a very practical problem. It's one of those very practical problems that has deep implications in the fundamental sciences. And again, I'm not going to go through this in detail and test your knowledge, but when people were thinking about how to make ideal engines and how do you idealize this very practical problem of a steam engine, you're thinking about different heat reservoirs, sort of temperature reservoirs, say a hot reservoir and a cold reservoir. You're extracting work from that reservoir to move your locomotive forward, and you're discarding, there's waste heat in this process. And when you think about this, and Carnot and Clausius are just two names that I will throw out that were sort of fundamentally thinking about these abstract engines, you notice, without giving it a name yet, that there's a quantity that we'll call sort of small changes of heat over the temperature. And over the cycle, paying attention to this quantity is very important for understanding the fundamentals of the cycle and the efficiency of the cycle. And now we give that name, a name to that quantity. We call it changes in entropy. So this ds here is related to these small changes in heat that happen across the reservoir. And out of this sort of very practical notion of thinking about engines comes something that we call the second law of thermodynamics. That is, the entropy change in a process either remains the same or grows. The entropy never decreases in an isolated system without energy influx. This law gives rise to our notion of time, the notion that things are different in one direction as opposed to the backwards direction. And I just want to pause for a moment so that everybody understands how crazy this is, because there is no notion of difference in time in our fundamental laws of the universe. This is a fundamental law that is emergent. Our laws, our standard model of particle physics, our model of general relativity, all of this has time reversal symmetry. But when you put a bunch of material together, there's a new emergent quantity, entropy, and changes in that entropy are only positive. And I think that's a good sort of starting place for the rest of our discussion, and that's where entropy was born.
Thank you so much, Greg. Wow, so that was a big finale for it. So there is a lot of things going on from entropy that matter. I guess Esther wants to take from here, right? Oh, your mic, Esther.
Good again. My apologies. Yeah, if possible, I'd like to add a few things, because where Greg left off, that is exactly where I usually start. So we have the second law of thermodynamics, right? That says that entropy in a closed system stays the same or increases. So entropy, and we'll probably get to that later, you can see that as a form of disorder. There's more to it, but we'll get to that. So basically, what is stated is that in our universe, entropy, disorder, disorganization can only increase. And yet look around you. So look where we are. Look at this world. This is not a disorganized world. It's a very orderly world. So when you look at the history of the cosmos, Earth, life, and humanity as a whole, then that is actually one of the first questions that strikes you. So if we live in a universe dominated by that second law, where does all the order around us, where does that come from? And there are a few answers that have been given by colleagues in my field. I'm not sure I should get into those right away. Perhaps it's a good idea to dive into what entropy is a bit further first. But I just wanted to add to this idea of this second law, because it means so much for history in a way that you probably, you don't get out of regular history books.
Yeah, and I'm also thinking like entropy does, even though it's a concept everybody has interacted with, it's also a bit of a concept that a lot of people have only a surface level knowledge of. There is like one example I can think of where a lot of people know about it. You get it in a bunch of like, pop science documentaries called Maxwell's Demon. Greg, can you tell us a bit about it?
Sure. And I think this will provide a nice link to Christian.
Yes.
So let me share. Okay, we're back on the slide. Okay, so just to remind you where we were, we had a definition of entropy. These changes in entropy are ds equals dq over t. And when people started thinking about the emergence of this law, which again isn't in the microscopic dynamics, Maxwell was the first one to notice that it seems like you can violate this with what he called a Maxwell demon. let me jump here. So, and just to give you an idea for how long this has been bugging people, and it still bugs people, right? We think we have this kind of, this demon sort of exorcised, I think is the right word. But it's a really interesting question. And let me take you through. So Maxwell talked about a general demon that long ago. And then more recently, in the last 100 years, there was a particular clean demonstration of this demon, and that's the Szilard. It's named after the person who talked about it. And let me just describe it, because I think it's pretty clear. So this squiggly creature here at the top is a demon. And imagine you just have one atom in a box. Okay, it's bouncing around, right? And you have a partition that you can move. Right? You can close off that box so it's only half as big. So you watch the atom and you wait until the atom's in one side of the box. And then you close the partition. Right? So now that the atom is bouncing around in half its volume, now you attach some sort of pulley system to that partition and you let the partition expand. Right? Takes you over to the bottom left panel. And now the partition has expanded. You've extracted work by lifting this, by letting the piston lift this weight. Seems like, and we can go through back to your formulas that you might remember from class. We can go through and calculate all the work done in every one of these little steps. But at the end of the day, across these whole 4 steps, across the whole cycle, you get kT log 2 joules out of this work, out of this cycle. But you haven't changed, it doesn't seem like you've changed the entropy because you're back to the exact same state. This would be a violation of the second law. Okay. And I want you to remember the log 2. That's going to be really important, and that's going to be something that I think Christian can say something about. And just to give you you should think about this as a paradox on your own, but the resolution of this demon paradox is that once you get back to this state where the atom now has the full volume again, you're not actually back to the same state until the demon erases their memory. And that erasure of memory is what generates entropy and keeps the second law intact. It generates heat. Okay, so the resolution of Maxwell's demon leads us much closer to the connection between thermodynamic entropy that we get out of a cycle like this and information entropy, where we think about bits. And I think I'll shoot it over to the organizers and see where they want to push us next.
Yeah, it seems like a good time to have Christian introduce his expertise. But before we do that, we did get this really eloquent question from the audience. I'll just quote it verbatim. So entropy is an emergent property which determines the arrow of time. Without entropy, no history? Question mark.
Me?
Yeah. Yeah. You introduce the concept, so it's on you now.
All right. There are 2 important answers to this question. Entropy breaks the invariance between going forward and going backwards. Okay, that's what the second law does. You need more information to understand why we, for example, remember the past but not the future. And that takes us deep into the idea that that the universe actually arose from a low entropy state. So entropy, the second law breaks the time reversal, but it doesn't tell you that we started in the past with a lower entropy state. Okay. So that's why I'm saying there's a lot in this second law.
Yeah, this definitely raises more questions, at least in myself, I'm pretty sure also in the audience. I want to give a cue now to Christian without going down the rabbit hole in his entropy and time. Because you, Greg, have been mentioning information during the Maxwell Demon paradigm. Information is also a big concept related to entropy, and Christian can tell us more about that.
Yes, definitely. Thanks. Let me also try to share my slides. I actually have one slide only. Do you already see something? So, can somebody confirm? Do you see the slide?
It says Christian Schaffner has started screen sharing on my end. Alvaro?
Yeah, I can see a black screen where it says that.
Black screen. Okay. That's I guess not what I want. Let's see. Let's do this differently.
I have the slide if you want me to share the screen.
Yeah, I'll give it one more try, and otherwise you can do it. Share my desktop. Do you see it?
Yeah, it's here.
Do you also see my pointer?
We also see your
Yes.
pointer.
Excellent. Okay, so yeah, I'd like to come back to this formula that Greg has already showed you partly, and I also point out it's the same formula. I mean, if you remember back in the days, your rules about logarithm, then like you see this 1 over px, this is actually equal to the minus log of just px. And yeah, this is kind of the formula that came up or that was written down by Claude Shannon. And Claude Shannon is the father of information theory. And basically the whole course that I give about information theory is about half of a paper he wrote back in 1948. So it's really amazing, like that in this kind of paper, he sets out so many very important concepts. Among others, like he defines the word bit. I mean, so something that has become a very fundamental unit in all of computer science and beyond.
Sorry, Christian, can you say briefly what is a bit?
A bit? A
Yes.
bit is just like the basic unit, which is either 0 or 1. So that is a bit. And then we are used to bytes, which are 8 bits together. And so 1 byte is usually like how you encode a character. And then we know kilobytes and megabytes and gigabytes and terabytes. So those are like orders that we quantify the amount of information, or the amount of bits one can store, for instance, on a hard drive or on a telephone. And yeah, so Shannon Entropy, I'd like to spend a little bit of time explaining this formula to you. It's usually denoted by H in information theory, and it's a property of a distribution. So we have Px is a distribution. Think of it in very simple cases, either like half-half, for instance, if P0 and P1 are both 1/2, then we have what we call a uniform distribution. Both outcomes, 0 and 1, are equally likely. Or here's another example of a distribution where just P0 is 1 and P1 is 0. So you have certainty that the outcome will be 0 of that. And of course, you can have anything in between these two, and you can have distributions with more than 2 outcomes. These are just simple examples. And what the Shannon entropy does, it associates a number, a real number, with a distribution. So, and it basically quantifies how uncertain you are about the outcome. And how does this work? Well, let's start at the innermost part. So this 1 over px, it basically tells you, it's a measure of how surprised you are if you see a certain outcome. And so this is, you can really see this as a surprisal value. And it's just the inverse probability. And it's pretty clear that if you see something unlikely, if you win the lottery, then the probability of this happening is very small. So you're really surprised if this happens. And if you have certainty, if you know already the outcome is going to be 0, well, then you're not very surprised. And then this will be actually a small number. And now the crucial thing is this logarithm. This is basically just measuring the surprisal, you're measuring that in bits. So here's the log. It's just a kind of a different scale in measuring how surprised you are. So that's how this logarithm comes in. And then what you do is you take the average of the possible outcomes. So in fact, this formula is really just the average surprisal value measured in bits. And we can apply this to our examples. Of course, you can go and plug in these numbers. But in this case, where you have a uniform distribution, then you're exactly 1 bit surprised on average if you see an outcome here, because every outcome has probability 1/2. So this becomes 2. If you take the binary logarithm, then this is just 1, and the average between 1 and 1 is 1. So you actually get the Shannon entropy of the distribution. So this number associated to distribution is just 1. And this says that you're kind of 1 bit uncertain if you see a fair coin flipped. So this is like a coin flip you can do, and you're kind of 1 bit surprised by every outcome that happens. And this generalizes to more coins. So if you flip several coins, and you see, for instance, you flip 10 coins and you see them all coming up heads, all of them, then you're exactly like 10 bits surprised that this happened. And in the contrary, if you kind of have a very biased coin, then no matter how you flip it, you always get heads. Well, then you already know the outcome. And if you plug in these numbers, you have to be a little bit careful, because mathematicians really don't like to divide by 0. So if you do 1 divided by 0, then it's actually officially not defined, but because you have a 0 here in front, that's kind of stronger. So if you take the limit for p going to 0, then you actually get a 0 here. And so you actually, the whole thing is 0. And it's really telling you that you're not surprised at all. There's no uncertainty in this distribution. And therefore, you know exactly what's going to happen. And here's a little graph that is very important in theoretical computer science, because it does many things. But this is just kind of the interpolation between the two. So this is assuming kind of a biased coin. And the extreme cases are shown over here. If you have a fair coin, then the probability of p0 is 1/2. And then you end up with exactly 1 bit of entropy. This is here. And the other extreme case is if the coin is biased in one way or another. And so if the outcome is, if p0 is 0, well, then p1 is 1. It's the inverse, because they have to sum to 1. And then you get this kind of curve. So this is kind of showing for a biased coin how big the entropy is. So this is kind of the beginning story of the first thing you learn if you do information theory. And the surprising thing that we'll get back to it is that this quantity, even though it looks like, well, okay, you can define it that way, it just quantifies so many interesting related problems related to compression and to channel coding, etc. So that's kind of the main contribution of Shannon. I think I will get back to that a little bit later.
So definitely Shannon entropy redefines the expression a bit of a surprise, I guess. I want to know more about what entropy does in your line of work, Christian, because you are a cryptographer, right? So
indeed,
both a quantum cryptographer. So both in the quantum world, there is a lot of uncertainty and surprise. And you were talking about information. That's what cryptography is about. It's language and computation. I would like to know a little bit more about that.
Yes, indeed. So for me, entropy and the related notions of like conditional entropy, and also there's something called mutual information, and all these things are defined in terms of entropy. It measures how much information, for instance, in our case, an attacker has about a certain system. So, for example, there could be like a so-called key distribution protocol going on. There's two parties that talk to each other. And then there's an eavesdropper who kind of overhears what these parties are saying. And they can try to extract some information from it. And what you want to argue is that in the end, when the protocol is finished, the eavesdropper does not know anything about the outcome of the protocol. For instance, if the parties want to agree on a key, then this key should be secure with respect to the eavesdropper. And with respect, and so formally we capture that by saying that the entropy that the eavesdropper has, given all the side information that the eavesdropper collected during this protocol about this final key, should be high. It should be a lot of uncertainty, and the eavesdropper should be left with a lot of uncertainty about what that key is. And so this gives me a concrete mathematical tool how I can prove the security of such keys. And things get really exciting when we actually consider quantum protocols, because then the players are actually exchanging quantum information, and the eavesdropper ends up with quantum side information. So we actually kind of have to mix in, or we have to generalize the notion of Shannon entropy to the quantum setting, where we actually have to define the entropy of quantum states. And so often we consider this kind of notion, like how much uncertainty you have about the classical, about the standard distribution like here, but given quantum side information. So you have to kind of talk about the correlation between classical and quantum information. So that's kind of my daily bread and butter.
Yeah, so I also wonder about this one thing, because you're also talking about like how you can encrypt information, and how, for example, with your quantum passwords, you want stuff to be as random as possible, which I think all of us can intuit if we ever went to a website and, you know, you don't want to have your password be ABC, but you just some kind of complete mess of characters. But I'm also thinking of like a very good physical example of that, and I think some people in the audience already can guess that one of the best examples of just locking away your goods would be to throw it into a black hole. Greg, you have a little bit more of a physical background on this. Can you describe to us how entropy is related to black holes?
Yes, I will do this very heuristically. Let me go back to my first slide. Share. Okay. So at the end of this particular musical sequence, entropic musical sequence, is a very famous formula, which I didn't talk about yet. This was the idea discovered 50 years ago that black holes, and for those in the audience that don't know, so a black hole is a special, formally it's a special solution in general relativity where matter has collapsed so strongly that there's what we call an event horizon, which is a region in space-time beyond which you can know nothing. No light can escape that, no information. Well, that's a contentious issue, actually. So let's say, at least in classical general relativity, nothing can escape that region. That's why we call it. It was the name black hole, I believe, was coined by Princeton physicist John Wheeler, who has a real knack for these kinds of things. And you will notice that, so this formula I'm talking about is in the center here. And just so I walk you through what the symbols mean, K is, actually, I think K is just a constant. A is the area of the black hole. A is the area of this event horizon, okay? And it's in units of the Planck area. So this is a dimensionless number. So LP is the Planck length. And the idea is simply in a black hole. So first of all, the notion that a black hole has entropy seems really strange, because unless we take Christian's view of uncertainty, in the thermodynamic case, this seems really strange because the black hole is just a solution in general relativity. There's no thermodynamics, right? So, but nonetheless, if you go through the original, so Bekenstein was sort of the original founder of this idea where you're thinking about, well, how do black holes collide? And if you think about the mass of the black hole, then if two black holes collide, the mass only can increase. Sounds a little bit like the second law, all right? And the notion that black holes have entropy and therefore temperature and so on, they radiate, that's Hawking radiation. The only real way to reconcile that with our understanding of entropy is to take Christian's notion of information theory really seriously in physical systems and say, what we're measuring when we see a black hole entropy is what we don't know because it's behind the event horizon, right? It's telling us that there's something extremely important about uncertainty, which is sort of what entropy formalizes uncertainty in information theory. By the way, you don't just have entropy in black holes, but you can have another special kind of space-time, which is, maybe this is a little technical for people, but it's really simple to understand. You're constantly accelerating. That's it. It's called a Riddler space-time. And if you're constantly accelerating, that space-time will also have an event horizon, and therefore will have an effective temperature and an effective area related to that event horizon. So in black hole thermodynamics, you really start to see these very strong connections between uncertainty, what you can't know because degrees of freedom are hidden from you beyond the event horizon, and information theory. I think I'll leave it at that.
Well, thank you for, well, pardon upon compressing all of that information regarding entropy and black holes. We've now been offered like two examples of entropy, information entropy with the rather straightforward logarithm equation, also entropy in the form of black holes, which is just a linear equation, which is surprisingly straightforward and direct to deal with. But there's also a bit more of an interesting case. For example, we're also talking a lot about organization, disorder, chaos, and those words aren't just used in a scientific department. In society, they're also used. And this is a part where I think Esther would make a great fit for telling us about entropy and, well, how it works with people.
Yeah, so that is one of the things that I think is exciting. So there are these very specific uses of entropy that we heard about, but you can also indeed generalize it and treat it as a kind of disorder that is very much related to this uncertainty, because you could see disorder as a state in which you don't know a lot. You have a lot of uncertainty about, well, the exact microstates that the system is in, something like that. So if you treat it like that, and if you think about the development of that kind of disorder, disorganization, is a system that you don't know, well, how it looks like at a micro level. If you think of it like that, then you can suddenly sort of apply it to all of these different fields. So you can apply it to physical systems. You can, of course, apply it to life. I think Greg has been working a lot on that. Perhaps he can talk about that a bit later. But you could argue, okay, you can perhaps also apply it to social systems, because social systems are also, well, organized in a certain way, in a very specific way. There's lots of ways in which you can have people interact randomly, but the way it generally happens, the way we're interacting now, that's a very specific way. So in that sense, it's very ordered. And you could wonder, I kind of already mentioned that, if you look at big history, the history of everything from the Big Bang to today, you see, well, the development of a certain kind of order, at least, despite this second law. So you could wonder, okay, at all of these different levels, the level of the physical world, the biological world, the cultural world, how does that work? So why is this disorder, this organization, why is that developing despite the second law? And there are several ways to look at this, I guess. So I have colleagues who have argued, okay, what you need, that's also related to Maxwell's engine, that we'll perhaps get to that. What you actually need is energy flowing through a system, which ensures that matter gets organized in a certain way. And it also leads to, let's say, the development, the dissipation of energy, and the creation of greater entropy elsewhere. So it doesn't violate the second law. And as a result of this energy, you get a system that is organized in a certain way. So people like Eric Chason from Harvard University have worked on that. And I also have colleagues at the University of Amsterdam who think, okay, well, you could also argue you add information to the system to get it organized, which is related to energy. And you can see that happening, right, throughout big history. You add information to a system, and then it suddenly becomes, well, life, or it becomes a brain or culture. Things that are, again, organized in a very specific way. And if you look at things like that, you can perhaps start to well, see patterns, think of comparisons, see connections, compare these transitions where information is added to the system and a new level of organization appears, and ask questions about that. So are they similar or not? If they're similar, what does that mean? Can we learn things from that? Can we be inspired by that? And all of these things, I think, give us a deeper understanding of how the world around us, how that came to be, which I think is an interesting question I would like to know more about. So that is how you can use that concept of entropy in big history to come up with these overarching patterns and questions and connections that surprisingly are, well, just becoming interesting to many scientists. I think, Greg, you're working on somewhat similar questions. I'm not sure, but you're coming from the the point of view of physics, and I'm coming from the point of view of natural history, basically, which is more descriptive. And I think that these kinds of approaches, well, are emerging. They haven't met everywhere just yet, so that would be very interesting to see if we could sort of combine these things in the future.
Yes, so thank you, Esther. You brought life as a entropy, the entropy point of view, and as a biologist, I started to realize later on in my career things about biophysics and how life is actually pretty good managing information and almost defies the second law of thermodynamics. So up to some point, life is like a Maxwell Demon. Is that true, Greg? Is life breaking the second law, or is getting close?
I don't think life is breaking the second law. Esther put it very well. We are driven dissipative systems. So you take energy, sunlight's coming down on the plants, we're eating the plants, or we're eating the animals that eat the plants, and we're dispelling waste heat, we're dissipating energy, but we get to organize ourselves because of that process. Well, as long as we have a source of energy and a place to put out energy, we can self-organize without violating the second law in any way. That's the answer. Now, just to add one more wrinkle, connecting information and life and entropy, you could ask, and people are starting to ask, at the very fundamental level, replication of your DNA, of genes, does some version of the second law of how close you can get to be to a reversible process, does that provide a fundamental physical bound on which life has to sort of come on top of, and how close does life get to that? We often, I think, mistakenly think of life as sloppy. It's not. It's complicated. And when you look at a complicated system through a small lens, you don't see all the patterns that Esther was talking about, for example. So here might be an example, if you look closely at just a particular process like replication, that you see life actually sitting right close to the physical the bounds we know from physics. And I think that's a really interesting conjecture to see if that's true.
Yeah, we've also gotten a question from somebody from a field I didn't actually expect to get one today. We got somebody from the economics department. Yeah, I have no idea. I would have told you all to get suits if I expected them, but to sum it up, they're asking, and I'm quoting them verbatim here: computers and robotics makes our lives more precise in every field thinkable. Small mistakes are eliminated in the end, it seems. The faster and powerful they become. Does this mean humankind is bringing entropy down in this way, so this technological advancement? This is an open question. The person who feels confident about answering it, have your go at it.
I see here an analogy between this and how evolution in life has been maybe bringing entropy down. So maybe there is a comparison here, side to side, in those two systems.
Perhaps Esther, you want to talk about it, considering your knowledge of the whole information revolution?
So I didn't quite get the second part because I couldn't hear properly what Alvaro was saying. I'm sorry. Can you repeat that? What you mentioned, Alvaro?
Yes, for sure. Sorry. What I said is that I see a side-to-side comparison here in between how we are improving our computers into, well, maybe bringing entropy down, as the question says, and how evolution has made information processing more effective and cheaper in the end, right? How a cell reads DNA and how a computer processes information, it has to be very effective, very cost effective.
Okay, yeah, I can respond to that, but I don't think I have an answer. What I can say is that indeed we have this idea in big history that you need energy to create this kind of order. And you can calculate that. So you can look at systems and you can see how complex. That's slightly different than ordered. It's complexity, I'd say, is a very specific type of order, but it's a type of order. But you can look at how complex systems are and how much energy you need for that. You can do these calculations, and then you actually see that throughout big history, you get these systems that are more complex. So from non-living systems, you get life, you get more complex life, you get colonies, you get groups of people that are connected throughout the world. And indeed, these things that we perceive as higher levels of complexity do use more energy. So those are things that have been calculated, that those ideas have been around for a while. But when it comes to information, at least in the field of big history, I think we have a lot to learn from all of these different disciplines who have come up with ideas about that, including information theory. And we actually only just started thinking through what these ideas mean for these big transitions in history. So for the emergence of life, the emergence of complex cells, multicellularity, etc. Because you do see that there are these big shifts in information processing. So the emergence of the genome, the emergence of, I already mentioned brains, of human culture, and also machines that can compute things and perhaps even learn to learn themselves. And we're just starting to apply those ideas, some of those ideas, to these different transitions to see if we can come up with some similarities. And there are these tantalizing ideas that pop up every now and then. So ideas about efficiency, ideas about connectivity, about the topology of networks and how that is influencing this whole process. But we're only scratching the surface, really. So I just don't know what to do with these ideas just yet. We formed a group of people at the University of Amsterdam, and we're brainstorming about it from time to time whenever we have time. And there will be another run of this Information Revolutions course, which is really an experimental honors course, where students can come up with all kinds of ideas about these kinds of connections and the role information play and between these big transitions in life and humanity, human history, and the role information plays in that. So hopefully that will generate some new ideas, which will feed into this discussion that we're having, which at this point is still very informal, but it's fun. So I don't know. perhaps Christian or Greg know. That would help me a lot.
I don't really. I mean, I have some idea, for instance, about the genetic code. I've done some work on that as well, and it's amazing, kind of how there's some error correction built into that system. So somehow how that came along. That's really one of the things of the big kind of unanswered question. No? Like how can you get there from very basic systems? So yeah. But this sounds great. I mean, I'm happy to contribute in the sense of like explaining what we know from the computer science side of things, no? Like how we use information and the entropy and what these kind of what the operational meanings of these things are in terms of computation. I think that's a very interesting lens to look at these bigger development questions. Yeah.
So I also think now that we're heading more to the end, that Greg has some unresolved issue regarding the whole Maxwell's Demon that we've been pestering the audience with. So Greg, can you strike him down? You're muted.
Strike what down?
Maxwell's
Sorry,
Demon.
Strike the demon down. Kill the demon.
Kill the demon.
Okay. So let's do. And here. Okay, I think put all these in. Okay. So now we're getting towards, I think, the end of our hour, and we'll talk about the demon first, but then I want to put this in broader context. And so, as I mentioned, when we go around this simple cycle, and you can all do this as an exercise on your own, you come up with an amount of work that is KT log 2. The log 2, of course, is coming from the fact that the demon made a choice it knows which side of the partition the molecule is in, right? That is the knowledge, that is the information that the daemon still has that has to be erased before this cycle can be repeated. All right. So the erasure of that information is, the idea that erasure of information must cause some heat to be the connection between heat and erasure, heat and information, is the resolution of this daemon, and it links information theory and thermodynamics in a very deep way. It links sort of the loss of information with the generation of heat. And to put this in what I think is, at least from my perspective, the broadest context, the formulas will differ. If I go back to this, these different formulas, from thermodynamics to statistical mechanics to information theory to dynamical systems to other formulas, the entropy will vary a little bit in how we measure it. There are different forms of entropy. There's differences in entropy that Krishna alluded to in information theory. But to me, the unifying characteristic of all of these is uncertainty. It's the quantification of uncertainty. And you don't really have thermodynamics without uncertainty, because a mole of gas isn't described by temperature, pressure, and volume. It's described by 10 to the 23rd velocities and positions of those particles in the gas. You don't know all those things, or you choose to be ignorant. And that's sort of the origin of uncertainty in thermodynamics. You don't know the microstates of the system. And I think that idea of uncertainty, whether it's black holes or other things in our world, the reason why entropy is so powerful is because uncertainty is so prevalent in our world. I'll end with that.
Yeah. Also, we usually have a decent planning on how to end these kinds of editions, but we've gotten like a lot of really high quality questions. One of the more, I guess, pointed ones, and this is probably hitting close to home for Schaffner. I'll just quote it verbatim for the audience. Shannon information is not a physical quantity, has no physical units, thus cannot appear in substantial physical laws, thus has nothing to do with black holes or Maxwell's demon. What's your view on that, Christian?
Yeah. I think I will pass that one to Greg, actually.
Okay.
In a sense, it is a quantification of uncertainty in a distribution. So the units are bits. So it's kind of a measure of how surprised you are. But of course, it matters what you're measuring. So, Greg, maybe you can chip in.
Right. So I will answer that by saying that units are a choice. And it happens to be that we have Boltzmann's constant, which in thermodynamics and statistical physics, you're used to seeing Boltzmann's constant in front of your P log P as your measure of unit. But that's really a choice of how you measure. It's not fundamental. So I don't see a fundamental distinction between due to the notion of units between entropy in the information theory sense and entropy in the thermodynamic sense.
Now, there is another question that relates to what Esther was talking about these sockets of chaos and order in the universe, and goes like this. So on the one hand, entropies cause a dissipation of energy in the universe, yet when we look at organisms on Earth, including animals and trees, we see a sort of compression of energy. Since these organisms are highly efficient in absorbing energy, how can we explain this dichotomy?
Again, I don't quite understand the question in the sense that an organism, but also a society, of course, takes in energy from the environment and then uses it to organize itself in a certain way and gets rid of it again, but it gets rid of it again in a slightly different way. So it's less useful energy, right? So getting back to this early definition of entropy, you take in high quality energy, you get rid of low quality energy, it's dissipated energy, and that means it's higher entropy. So that is how that works. You're dealing with energy flows through a system that flows from high energy to low energy. That does work. It organizes something. It ensures that it's orderly and you have less ways to be ordered, organized, and more ways to be disorganized. So that is how that relates to uncertainty again. And in that process, you get rid of the additional energy, which is related to higher entropy. I'm not sure if that answers the question though, because I'm not completely sure if I understood it right.
Yeah, I think so.
Okay.
What I understood is that these self-organized complex systems, such as life or societies, are better increasing entropy than the universe could be without them. So these order systems, like life, is actually increasing entropy, even though itself is order. Right?
It's increasing entropy elsewhere,
Outside.
even though
Okay.
it's lowering its own entropy. Yes.
Exactly. Okay.
Yes. So as a whole, the system as a whole, in the system as a whole, the entropy does not decrease. It's only, let's say, in the system that is not closed, that is benefiting from this energy flow, where you have a lowering, but elsewhere you get higher entropy, and that sort of balances each other out.
Okay. Nice, thank you. Well, we got two more questions. One is from us, Saad and me, to the moderators and to the audience. It's kind of a food thought. But before going with that, we want to go with the last question we have from the speakers. It's a pretty good one. It goes, how is it to explain that the universe started in a state of low entropy? Who wants to tackle that?
Greg, would you like to?
I think that's a really deep question, and there's no simple answer to that. No.
Well, that's, yeah, fair enough. We're also at the last bit of the talk. Then, sorry for the audience. I guess that's a really detailed answer that you need there. We are going to go with our last questions. That's from us to the speakers. It says, can entropy be described as just some very useful math tool, or should we take it as an actual force of nature?
Well, since I'm unmuted, I'll start. Do you like thermodynamics? If you think thermodynamics is part of nature, then I think you have to admit entropy in its informational form is part of physics and part of nature.
I would agree. I guess it's a characteristic of our universe, and it is something that all of the systems that we see around us sort of try to combat. I'm not completely sure if that makes it a force, probably not, but it's something that's, yeah, that we do something with, I guess. But it's a battle we ultimately cannot win, right? So entropy will win in the end, according to most scientists.
I mean, from my point of view, it is more like a tool, but that's just like influence from my background. But of course, I think in the bigger picture, it is a useful concept to understand what's going on in nature. So maybe as Esther said, maybe it's not a force on its own. It's not something that drives the world, but it's a very useful concept to kind of understand what's going on and what has been going on so far and what will be going on.
I want to add one thing, because I think it's to Christian and really important. If you study information theory, entropy is not just, Shannon entropy is not just a measure of uncertainty. It is the measure, right? And
definitely.
I think that's important to know. It's not like there's lots of measures you could build of uncertainty. The variance of a random variable is a measure of uncertainty. Yeah, but it's incomplete. And I think you should, so I would point people to Christian's class, actually, to learn why we think that entropy, this form of entropy, not just uncertainty, but this particular measure of entropy is actually fundamental.
Yes. And there's even kind of mathematical reasons for it. So you can kind of, if you put down a few axioms that you want to have fulfilled, then you will end up with exactly that notion of entropy. So it's not a coincidence that it's exactly that formula that kind of answers a lot of questions, very natural questions that come along. Indeed.
Perfect. Thank you so much. Well, I guess we're gonna end the talk here. It's a really interesting topic and really deep. We could go on for hours, I believe, and every different field have a different view on it. I hope we help the audience with whatever the doubts were. We want to thank the speakers. First of all, thank you, Christian, Esther, and Greg, for taking your time and for your knowledge.
Thank you for organizing this.
Yes, thanks for the invitation.
Much our pleasure. We want to thank, of course, the audience for being here with us, and SPY 5 in 20 for making the tech support and bringing us their platform to do the talk. And you want to add something else?
No, I think you were quite complete, but for the one student that we ended up not being able to answer your question, our apologies for not having enough time. But for the rest, I think today everything went quite well. And in addition to that, I wish everybody a good summer vacation, especially after this whole year. And well, that wraps it up.
Go generate entropy.